So this video is on classwork, chapter 12, classwork number 2, 12-1 to 12-14 to 12-19. So in this situation, we're learning about something called permutations. How can I count arrangements? So there are many kinds of counting problems. In this lesson, you will learn to recognize problems that involve arrangements. In some cases, items will be repeated, but in others, they will not. Permutations equal different arrangements of objects chosen from a set of objects without repetition. So different arrangements without repetition. So on 12-14, Jasper has enough money to open a savings account at a credit union. When he goes in to open the accounts manager tells him that he needs to select a 4-digit PIN number. She also says that he cannot repeat a digit, but that he can use any of the digits 0, 1, 2, all the way up to 9 in his 4-digit PIN. How many different PINs are possible? So for this, again, it's a 4-digit PIN. He cannot repeat a digit, and he can use the digits 0 through 9, okay? So when we're doing this, if we are trying to get a 4-digit PIN, okay? So 1, 2, 3, 4. The first digit, there are 10 ways to get the first digit because 0 through 9 is really 10 different numbers, okay? Now that the first one is picked, there's 9. Now that the second one's picked, there's only 8. Now that the third one's picked, there's only 7. And so we're going to work this out. Now, the other day, I was talking to you guys about this is really 10 factorial, but what's missing from the 10 factorial is 6, 5, 4, 3, 2, 1. So if I divide this by 6 factorial, this is going to give me the same answer. Okay, this is going to give me the same answer. So 10 factorial divided by 6 factorial. And if I was to take 10 times 9 times 8 times 7, you see I get the same answer, 5,040. So there are 5,040 different PIN numbers. Notice that the decision chart for the problem looks like the beginning of 10 factorial. So this is what they're talking about, 10 times 9 times 8 times 7. But it does not go all the way down to 1. What is missing from 10 factorial in part A? Can you write the missing part in factorial? So we're missing 6, 5, 4, 3, 2, 1, or 6 factorial. That's what we're missing. And that's why I wrote it out like that. Okay. On letter C, how can you write the number of different 4-digit PINs and more concisely using factorials? So again, we could do 10 factorial, and what we're missing is 6, 5, 4, 3, 2, 1, or 6 factorial. And that gave us the same answer as when we worked it out for letter A. Show how you can use factorials to represent each of the following situations. Then solve the problems. 4 of the 5 problems involve a permutation, an arrangement that does not allow repetition, and 1 does not. Write your answers both as factorials and as whole numbers. Okay. So on letter A, we have 52 contestants. Okay, so let me just kind of highlight some of the big information. We have 52 contestants that submit an entry in the contest to choose a new school logo. In how many different ways can the judges pick the best logo and the first, second, and third runners up? So basically, we're going to be picking 4 different things. And once we pick something, we can't pick it again. So 1, 2, 3, 4. So the best, there will be 52 ways. Then after the best was picked, the first runner up, there's going to be 51. After that, for second runner-up, 50. And after that, for third runner-up, 49. Now, how can we write that? This is going to be 52 factorial divided by, and what we're missing is 48 on. So we're going to divide it by 48 factorial. So let me just clear this over here. And let me just make this a little bolder also. Okay. So if I did 52 times 51 times 50 times 49, you see what I got. Now let me do 52 factorial divided by 48 factorial, and you see I get the same answer. So they both are equivalent. And that is going to be 6,497,400 different ways that that can happen. Okay, on B. A volleyball team is sponsoring mixed doubles, okay, sand court volleyball tournament. And 16 pairs, okay, so 16 pairs have signed up for the chance to win one of 7 trophies. So there's 7 trophies total. How many different ways can the teams finish in the top 7 slots? So if I'm doing this, I can list 1, 2, 3, 4, 5, 6, 7. That's going to be 16 for the first, 15, 14, 13, 12, 11, 10, or 16 factorial over what's left over, or what's missing, I should say, 9 factorial. And again, if I was to put this into the calculator, 16 times 15 times 14 times 13 times 12 times 11 times 10, I get 57,657,600. Okay, so let me do 16 factorial divided by 9 factorial. And you see, I get the same answer. So this can be 57,657,600 different ways for 16 different pairs to get the top 7 spots. On letter C. Carmen is getting a new locker at school, and the first thing she must do is decide on a new locker combination. The 3-digit number, sorry, I meant to do that in the highlight. The 3-digit number is what she's going to be doing. So a 3-digit locker combination can be picked from the numbers 0 through 35. How many different locker combinations could she create if none of the numbers can be repeated? So none can be repeated, okay? So for this, we're trying to get a 3-digit locker combination. So 1, 2, 3. And when we're dealing with 0 through 35, that's actually going to be 36 choices. So this is going to be 36 times 35 times 34, or 36 factorial divided by 33 factorial. So again, 36 times 35 times 34, 42,840, or 36 factorial divided by 33 factorial, which gives the same answer. So 42,840. On letter D, for this one says how many 3-number locker combinations can Carmen choose from if 0, so if 0 cannot be used for the first and none of them can be repeated. Okay, so this one's going to be slightly different. So this is going to be a 3-digit number. No 0 for the first. So out of the 0 through 35, which is 36, there's only going to be 35 different choices. Now we're going to put that 0 back in. So now we have, because only 1 out of the 36 has been used. So now we have 35 again, and then 34. So this would really be 35 squared times 34. I probably would not write this one in, well, I mean, if you're going to write it in factorial, it would be 35 times 35 factorial, because of the 35, 34, divided by 33 factorial. I probably would not write it like that. I probably would either leave this one in a decision chart or write it as the 3 squared times 34. But all of these should give me the same answer. So 35 times 35 times 34. Okay, and obviously 35 squared times 34 is going to give me that. Or 35 times, and then I'm going to do a fraction, 35 factorial over 33 factorial is going to give me the same answer. So it's going to be 41,650. On the next one, how many 3-number locker combinations? So again, we're having a 3-number locker combination. Can Carmen choose from if she can use any of the numbers 0 through 35, and she can repeat them? Is this locker combination considered a permutation? Explain why you think that this is or is not. So in this case, we've got 1, 2, 3. So we're going to use the numbers 0 through 35, which is actually 36. We're allowed to repeat, so it's going to be 36 times 36 times 36, or 36 to the third. And 36 to the third is 46,656. Now, is this a permutation? No, it is not a permutation. Since there is repetition. If you can repeat, it's not going to be, repetition. Okay. On 12-16, a permutation is an arrangement of items in which the order matters. So here's some key facts about this. Okay, a permutation, order matters, and items cannot be repeated. Okay, so cannot be selected more than once. But I'm going to write it this way. Order matters, and no repetition. That's what's important. Okay, and this is for a permutation. Okay. So in this situation, it says, arranging the winners of a contest in order is an example of a permutation. At the right is a list of the license plate letter triples that you can make with the letters A, B, C. How is this list different from the arrangements a child can make on a line of the refrigerator door with 3 magnetic letters A, B, C? Make the list of arrangements that the child can make with the refrigerator letter magnets. Why are the lists different? Which one is a permutation? So in this case here, let me zoom in. You are repeating, okay? So we have repetition here, here, here. This one has repetition. This one has repetition. This one has repetition. These all have repetition. So all of these ones where we're repeating, that is not allowed in a permutation. Okay, this is not allowed. None of these ones are allowed in a permutation. Okay, ABC is okay, ACB is okay, CAB is okay, CBA is okay, BAC is okay, BCA are okay. So the ones I'm going to highlight right now in green, these ones would be allowed in a permutation where you have 3 letters that you're ordering, but you cannot repeat them. Okay, you're ordering those 3 things. So when they're talking about how can you list for a child on a refrigerator, it is those ones I just listed in green. So if a child has 3 magnets, an A, B, C, and they're trying to make air quote words, because a lot of these are not words, only one of them would be a word. Again, order matters, and there is no repetition allowed. So you can do A and then B and then C. And then if I have A again, then you could have the C and the B switched. Now, what if I start with the B? Okay, then I could have B and A and C, or I could have B and then C and A. Well, what if I start with the C first? I could have A and B, or if I have my C first, I could have B and A. So you see there are 6 different ways that can happen, okay? And this one here is a permutation, not the ones that are listed in the box. The ones that are listed in pink would not be a permutation. All the ones listed in the box would be all the different ways. If you were allowing repetition, including the green ones, that would be included. But if it is no repetition, it would only be those green ones. That would be a permutation. And really, this would be 3 spots, 3 for the first, 2 for the second, 1 for the last, which is 3 factorial, or 6 if I was to do that math. Now, the one that they listed here, okay, let me just kind of zoom. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 rows of 3. So 9 rows of 3 are going to give us 27. So that one would have been 3 different ways for the first, 3 different ways for the second, 3 different ways for the third, 3 to the 3, which is 27. So that is how we would have found them mathematically in both of the cases, okay? On the next problem, letter B, it says, imagine a group of 8 candidates. One will become president. So one will become president. So we have 8 candidates. One will become president, vice president, secretary. Now imagine a different set of 8. Okay, so it's a different group of 8, and 3 of whom will be selected to be on the spirit committee. How will these lists of 3 people selected from the 8 people be different? Compute the number in each list, which would be a longer list, which is a permutation. Okay, so if I am doing it for the school senate, we have 8 people. Okay, we've got president, vice president, and secretary. Okay, so we have 8 ways to get the president. We have then 7 ways out of the 8 left to get the vice president, and then 6. Or 8 factorial over 5 factorial. Okay, and so when I do this, let's say I do 8 factorial divided by 5 factorial, I get 336 different ways. Okay, now for the other one, what's going to happen is this is more like, well, so in this case, I'm not going to have a person repeat. Okay, that's the problem. So what's going to happen is, let's say I've got person 1, 2, 3, 4, 5, 6, 7, 8. I could have 1, 2, and 3 together. I could have 1, 2 and 4 together. I could have 1, 2, and 5 together. I could have 1, 2, and 6 together. I could have 1, 2, and 7 together. And I could have 1, 2, and 8 together. Okay. Now, let's say I have person 2. And the order doesn't matter here. So 1, 2, and 3 is going to be the same as 3, 2, and 1. But I could have 1 with 2 and 3, 1 with 2 and 4, 1 with 2 and 5, 1 with 2 and 6, 1 with 2 and 7, 1 with 2 and 8. Or I could have 2 with 3. Okay. I've already done 1 and 2 together with everybody. Okay. Now I'm going to do 2 and 3 with everybody. So I could do 2, 3, and 1, but I've already gotten that. So 2, 3, and 4, 2, 3, and 5, 2, 3, and 6, 2, 3, and 7, 2, 3, and 8. Okay. Now I could do 3 and 4 with everybody. So 3, 4, and 1. I don't have that one yet. 3, 4, and 2 I already have right here. So 3, 4, and I can't do 3, so I can't do 4 because that's repetition. So 3, 4, and 5, 3, 4, and 6, 3, 4, and 7, 3, 4, and 8. I can do 4 and 5 with 1 because I haven't done that. I can do 4 and 5 with 2. I haven't done that. I can do 4 and 5 with 3, but I've already done that. 4 and 5 with 4. I can't do 4 and 5 with 5. I can't do 4 and 5 with 6. I can do 4 and 5 with 7. 4 and 5 with 8. Okay. And so forth. This is how you can start listing it out. Now, in this case, when I'm doing this, let's see if we can do it in a faster manner. So I added an extra page at the bottom after the last page of this, just so I could write this out. If you guys want to do some of this work on your desk, that's fine, and just write the answer. But what I'm going to do is I'm trying to list 1 through 8 candidates, all the different groups of them where order doesn't matter within the group, because 1, 2, 3, and 3, 2, 1, and 2, 1, 3 are all the same. So I'm just going to kind of do it in this systematic way. So I'm going to do 1, 2, 3, 1, 1, 2, 4, 1, 2, 5, 1, 2, 6, 1, 2, 7, 1, 1, 2, 8. Okay. And let me do 1 with 3 now. So 1, 3, 4, 1, 3, 5, 1, 3, 6, 1, 3, 7, 1, 3, 8, 1, 4, 5, 1, 4, 6, 1, 4, 7, 1, 4, 8, 1, 5, 6, 1, 5, 7, 1, 5, 8, 1, 5, not 1, 5, sorry, 1, 6, 7, 1, 6, 8, and 1, 7, 8. Okay, so I've got 1, 2, 3, 4, 5, 6 here, 5 here, 4 here, 3 here, 2 here, 1. And when I add that up, that's going to be a total of 21 for that situation. Okay, let's say I start now with 2. Okay, so 2, I'm not going to do 2, 1 because my 2, 1 is already done in the first column in the red. So I'm going to do 2, 3. 2, 3, 4, 2, 3, 5, 2, 3, 6, 2, 3, 7, 2, 3, 8, 2, 4, 5, 2, 4, 6, 2, 4, 7, 248 to 5 6 257 258 267 268 278. So I have 5 4 3 2 1, and when I add that up, I'm going to have 15. So now if I do starting with 3, so 3 4 5 3 4 6 3 4 7 3 4 8 3 5 6 3 5 7 3 5 8 3 6 7 3 6 8 3 7 8. So I have 4 and 3 and 2 and 1. And so that is going to be 10. Now I'm going to start with 4. So 4 5 6 4 5 7 4 5 8. That's going to be 3. 4 6 7 4 6 8. That's going to be 2. 4 7 8. That's going to be 3. Sorry, 3 1 1 total. And so that is going to be 6. And you kind of see a pattern here. 5 6 7 5 6 8. That's 2. 5 7 8. That's 1. So that is 3. And then if I start with a 6, 6 7 8. And that's going to be a 1. And then once I do 7 8, I've already gotten everything. So let me just add these numbers up. Okay, so I have 21 15 10 6 3 1. And when I add that up, see, that's going to be a 4, so that's going to be a 10. Now we got a 20. We have a 41 and a 15. So that's going to be 56 different ways that can happen. 56 different ways. And if you're wondering, well, are you sure you got everything? Again, when I'm doing this, and I'm just looking at 1 2 3. 1 2 3 is going to be the same group as 3 2 1, as 2 1 3, and so forth. So there are 6 ways to arrange those 3 items. And I don't care about the grouping of them. I mean, the order of them. So there's only one for that particular 3 set of numbers. Okay. So let me go back up here where they asked us how many different ways can that happen. There were 56 different ways. So there's a lot less when in this situation than this situation. So this one has less, this one has more. So when there was order, there was more. When there was no order, there was less. Okay. And that's going to be important on something that we're going to be learning later in the week. Consider these 2 situations. The side of each situation is a permutation. Explain why or why not. Then compute the number possible for each situation. So on this one, writing a 4-digit number by choosing any digits from the numbers 2, 3, 4, 5, 6, 7, 8. So we've got 1, 2, 3, 4, 5, 6, 7. That's 7 different numbers there. And you can use digits several times. So this one's going to be not a permutation. It does have order, which is part of a permutation. It has order, but repetition's not allowed. Repetition not allowed for a permutation. And in this case, we had repetition. Okay, and they want us to compute this. So if we compute this, this is going to be 7 times 7 times 7 times 7, or 7 to the 4th. And when I do 7 to the 4th, I'll get back to normal. 7 to the 4th, I end up with 2,401 different ways. Now, the next part says making a 4-digit number by choosing 7 square tiles, each with the same numbers 2 through 8, but we're choosing 4 tiles basically. So there is no repetition here. So again, there's going to be 7 things. So this one is going to be a permutation. And the reason it's going to be a permutation is 2 parts: order and no repetition. Those are the 2 things that are needed for it to be a permutation. So again, 1, 2, 3, 4, there's 7 ways for the first, 6 ways for the next, 5 ways for the next, 4 ways, or 7 factorial divided by 3 factorial. And so when I do 7 factorial divided by 3 factorial, I get 840 different ways. Okay, so we need to understand the difference between these situations. Again, both of them ordered mattered. The top one here, repetition was allowed. That is going to make it automatically not a permutation. In order for it to be a permutation, you need order and you need no repetition. So these ones up here with the spirit committee, when I really had no order, that is not going to be a permutation. Okay, so this one here is my permutation. This one here is not a permutation. Okay. What are the important characteristics that a counting problem has to have in order to classify as a permutation? Write a general method for counting the number of arrangements in any problem that can be identified as a permutation problem. Okay, so for this situation, there is, so for a permutation, must have order and no repetition. Now, if I'm doing this in general, let's say I have n items for r positions or slots. What am I doing? I'm taking n factorial, which is the total, and then on the bottom, I am not using this number. I have that many slots. It's going to be subtracting them. So you'll notice up here when I did this, I had 4 positions, but this was not 7 factorial over 4 factorial. It's over 7 minus 4, which is 3. And up here, when we had 3 positions, it was, and we had 8 things we're picking, it wasn't 8 factorial over 5 factorial, it was 8 factorial over 8 minus 5, which is 3. I mean, sorry, 8 minus 3, which is 5. So this is going to be our formula for a permutation. Okay, so what is the formula? In part A of problem 12-15, you calculated how many ways judges could pick the logo contestant winner and 3 runners up with 52 contestants. The answer can be written using factorials as 52 factorial over 48 factorials. Where do these numbers come from? So the 52 factorial is basically the total number you are picking from factorial. And then the 48 is the total minus number of items you want factorial. So this is really 52 minus, and we were picking 4 spaces. So that gave us 48. And that's how I got my 48 factorial. On B, the logo contest situation can be thought of as calculating a number of possible arrangements of 52 elements arranged 4 at a time. Re-examine your answers to part B and C of problem 12-15 and use your answers to write a general formula to calculate the number of possible arrangements of n items arranged R at a time. So again, what we are going to do is we're going to take the total factorial, okay, which is this number factorial is going to go here, over, and then I'm going to go n minus r factorial, and I'm getting that r from there. And that's going to be the way you do it. So use your formula from part B to calculate the following. So in this one here, I'm going to go 7 factorial over 7 minus 4 factorial, or 7 factorial over 3 factorial. And then when I put that into the calculator, I see over here, actually, this is one we already did. That was 840. Here, 52 P4 is going to be 52 factorial over 52 minus 4 factorial. And so that's going to be 52 factorial over, let me zoom in a little bit, over 48 factorial. And we had done that one with the contestants. And that one we got 6,497,400. 497,400. And then this 16P7 is going to be 16 factorial over 16 minus 7 factorial. So that's going to be 16 factorial over 16 minus 7, which is 9 factorial. And when we had done that one, that was the volleyball one, we ended up getting 57,657,600. So we got 57,657,600 as our answer. Now, there is a button on your calculator and also here in Desmos. Okay, in Desmos, there's something that says NPR here. And so if I was to do 7 things for 4 positions, I get this answer here, 840. If I'm going to take 52 contestants for 4 awards, we get that same answer here, 6,497,400. And same with this last one, 16 P7. Now, if you are doing this on the graphing calculator, let me show you where you can easily find that. So if you're using our school calculator, 2 ways to do it. One way is to hit this math button. Okay, when you hit this math button, you're going to get this menu. And you see here, number 2 is your permutation. And here, number 4 is your factorial. You can actually use the arrow buttons, and instead of arrowing over to number, complex number, probability, you could actually go the other direction, go backwards. Starting here is going to go backwards to here, whichever way you want. I personally don't use that button. I use alpha and window. And when you use alpha and window, you're going to get these sets of choices. Here is your factorial that we're using on Friday. And then here is your permutation. Okay, that's how I personally would do that. And then when you do it, if you can either put the front number first, or you can choose it first and then put the numbers in it. It will work either way. Okay. Okay. Now, this next section is how many distinct ways so we're rearranging letters with repeats, okay, with repeats. How many distinct ways can the letters, so some of them have repeats and some of them don't. So we'll kind of see differences here. How many distinct ways can the letters in the word mash be arranged? Okay, so if we're dealing with the word mash, there are 4 letters. So pretend like this is Scrabble tiles, okay? So you've got 1, 2, 3, 4. 4 ways for the first, 3 ways, 2 ways, 1 way, or 4 factorial. That's also the same as 4P4, 4 things for 4 positions. All of these are going to give us the same answer. So if I do 4P4, you see I get 24, which is the same as I would get if I was doing 4 factorial. And really that would be 4 factorial over 0 factorial because we're not missing anything out of that. And 0 factorial is a 1. Okay, just kind of a side note. Let me get rid of that. How many distinct ways can the letters in the word sash be arranged? Why is this answer going to be different? So this is going to be a different situation because what's happening is we have this letter S. Let me highlight it instead of trying to circle it. We have this letter S twice. Okay, and it doesn't matter which S it is, it's going to be the same word. So when we're doing this, what's going to happen is it's going to change this order. Okay, so what's going to happen when we're doing this is when I'm doing this, what the formula is going to be is the following. You're going to take the total number factorial, okay, the total number factorial, which is all 4 of them, and then we're going to divide out the repeats, okay, the ways I can arrange these 2 items. I can arrange them 2 factorial ways. And I'm going to put this into my calculator and get my answer. Now, this really is 4 times 3. So this is going to give me 12 as my answer here for this one when I do work this out. Now, when we are doing this next one and we have SAS, we have an S1, 2, 3 times. So we still have 4 items. Okay, so we're still going to be having things ordered, 4 items ordered, but when I have this S 3 different times, it doesn't matter which S is in which position, they're all going to be the same word. And so I'm going to divide out how many different ways I can order those 3 S's. And there's 3 factorial ways to order 3 S's. And that's going to actually just end up giving me a 4 when I do that math. On D, express your answers to part B and C using factorial fractions with factorials, then numerators should both be factorial. Explain why these numbers make sense. So again, I've already done that up here. They probably wanted you to kind of list out the different ways you can get that to happen, like list them physically out. but what's happening is this 2 is all the ways that I can arrange the 2 S's. So this is the number of ways to arrange the 2 S's. And here this 3 is the number of ways to arrange 3 S's. So that's what they're looking for on letter D. How could you use fractions with factorials to compute for repeated letters when counting the number of arrangements? So the numerator is the number of ways. So the numerator is the total number of letters, factorial, divided by the number of repeats of a letter, factorial. Sasha wonders how many distinct ways there are to arrange the letters in her name. She thinks it's 5 factorial over 4 factorial. Is she correct? Now, what's happening is she does have 5 letters, so it's going to be 5 factorial on top. However, when we're doing this 4 factorial on bottom, yes, there's 4 letters that are being repeated, but there's only 2 S's that are being repeated, and then there's 2 A's that are being repeated. So when we're doing this, we're not having all 4 letters, how many ways we can arrange those 4 letters. It's how many ways can I arrange my S's? 2 factorial, times how many ways can I arrange my A's? 2 factorial. And when I work this out, this is actually going to be 5 times 4 times 3 times 2 factorial over 2 factorial times 2 times 1, if I'm doing it without a calculator. So this 2 factorial and this 2 factorial cancel out. 2 times 1 cancels with part of the 4, leaving me with a 2. And so when I work that out, I end up with an answer of 30. So hopefully this helps you out and gives you a little better understanding of factorials and permutations. So good luck on your homework tonight. I'm going to make a video for that also.